Okay, so welcome everyone. The quantum computers are coming. My name is Alasdair Collinson. I'm a senior software developer for Xenocor Technologies and blah, blah, blah. You don't really care about any of that, do you? There's one thing really that you have to know about me. I'm a nerd. I'm a huge nerd. In fact, I'm so much of a nerd that my colleagues call me a nerd. And there are, other computer scientists and mathematicians and physicists. Now, personally, I'm not a physicist, not at all. Last time I had any formal education in physics is ages ago. But I'm here, nevertheless, to speak about quantum computers. And the good news is you don't have to be a physicist anymore to get into quantum computing. It's the time now where being a nerd is sufficient. And that's really good news because in looking at you here, you're probably not going to need quantum computers for your job. Yet you're sitting here watching a talk on quantum computers. Chances are you too are nerds. Okay, so what is a quantum computer? Let's get started with the basic term. And the easier part of that is, what is a computer? Well, this is a computer, rather older than what you probably use, I hope. This, one could argue, is the first computer ever, at least the first electronic digital programmable computer, the SUSE Z3. And digital or binary is a big point there. When we think of binary, we normally think of zeros and ones, but that's not really true, is it? We don't have zeros and ones in our computers. We have two distinct states, and for what we care about, it could be a green circle and a red triangle. As long as they are distinct, that's fine. Now, computers nowadays work with transistors, well, smaller than those, more like this here, built into small chips. And the way that transistors work is basically that depending on their input, they either let a current go through or they don't. Two distinct states. Wonderful. And this is great for loads and loads of problems. I mean, the fact that where we are with computing technology nowadays is due to the fact that this is such a versatile tool. But it's not great for everything. And I'm going to show an example of something it's not great at. As nerds, you may be not that familiar with this, but nature. Okay, so nature is not binary. Let's have a look at a close part of that and try to determine where we have forest. So this part, that's clearly forest. This part clearly isn't forest. But what about that part? I mean, you clearly have some trees there, right? But most of it is grass. So where do we draw the line? When do we call it a forest? And that question, where do we draw the line? We have to draw an arbitrary line. We have to decide how much, say, trees per square kilometer or whatever counts as a forest. And when we have to draw such a line, when we have to make a decision, we are artificially making our world binary. Binary problems are great for computers, non-binary problems, not so much. Okay, so that's the computer part. I think we're all up to speed. Now the quantum part. So quantum, as you may have guessed, is based on quantum mechanics. Quantum mechanics was first introduced by Niels Bohr and Werner Karl Heisenberg. They worked together in the 1920s, came up with quantum mechanics and what they called the Copenhagen interpretation of quantum mechanics, named after the city where they worked together. Now, I'm not going to explain all of quantum mechanics, partly because, as I said, I'm not a physicist, and partly because even if I were, we would need more than the time we have available. So I'll give you an example. And the example is, imagine we have an atom. In fact, we don't care about the whole atom, all we care about is the nucleus here. And let's say that our atom is radioactive. What does radioactivity mean? It means basically that at some point it will decay, which means that part of it will radiate away. This radioactive particle, an alpha particle in this case, will leave the nucleus, and what remains will be some other element. So, assuming we have our particle, our atom, and we wait for a certain time. If we look at that particle, there are two states we could imagine it being in. Either it hasn't changed at all, or it has decayed, right? According to the Copenhagen interpretation of quantum mechanics, it can be both at the same time. That is, it can be both at the same time until we actually measure it. Now, don't be confused by those eyes. I'm not stating that there's any connection between consciousness and physics. Looking is one way of measuring it, but anything that relies on it being in one state or the other counts. So, nevertheless, this is a really, really weird thing to imagine. How can something be in two states at the same time? And so, Schrödinger here in 1935, he thought this was pretty weird, so he came up with a thought experiment showing how absolutely weird the interpretation was that Heisenberg and Bohr had come up with. In this experiment, which you may have heard of, he has a cat, and this cat is totally fine. It's healthy. It's not likely to die within the next hour or so of natural causes. And he puts this cat into a box. The cat, however, is not the only thing in the box. What else do we have? Well, we have a radioactive source of some kind. This is very similar to the radioactive atom we had previously. There's just more of them. And this source has been chosen in a particular way so that if 1 hour passes, the chance that any of it has decayed is 50-50. Okay? What else do we have? Well, there's also a flask filled with cyanide gas in there. Cyanide gas, of course, highly poisonous. It's better if the gas stays in that flask. But he added a fourth thing. He added a construction which consists of a Geiger counter that, if it measures any radioactivity, will use that hammer. And what will happen there? Well, dead cat. So, if we again imagine an hour passes, what are the states that we could have? Well, either the radioactive isotope has not done anything, it's not decayed in any way, and the cat is fine, or, well, the cat's dead. Two possible states. And according to the Copenhagen interpretation, we could have both of them together. We could have them at the same time. I mean, how can a cat be dead and alive at the same time, right? Schrödinger wasn't thinking of zombie cats as far as I can tell, but it's definitely a weird concept. And so he came up with an alternative interpretation because he did believe that the maths behind quantum mechanics was correct. He just thought that the Copenhagen interpretation was nonsense. And the interpretation he came up with is called the many worlds interpretation. Now, before I get into what the many worlds interpretation means, I have a small disclaimer. For us, for our purposes, the many worlds interpretation is a model. It helps us understand certain aspects of the topic. It's really good at that if it's chosen well. But models have something else. Often, models are wrong in many ways. And that's fine as long as they're wrong in ways that we don't care about. And the many worlds interpretation, for our purposes, is right in where it counts. It may or may not be correct in all, overall, I don't know, I'm not a physicist, and I think even physicists are unsure about this. It's certainly right in the ways we care about. Okay, with that disclaimer out of the way, what does the many worlds interpretation say? Well, it says, first of all, take everything there is, the world, the galaxy, the universe. I couldn't find a picture of the universe, but the galaxy here will work. And in this universe, among other things, you have your cat. Now, when this radioactive event happens, this quantum event, so to speak, you don't get your zombie cat situation. Rather, what happens is that you get two universes. And basically, they're carbon copies of each other with one exception. And that exception is the result of your quantum event and everything that followed from that. So, in one universe, you have a live cat. In one universe, you have a dead cat. And of course, this can happen again if you have another radioactive event, or quantum event, giving you 4 universes, and again, giving you 8 universes. You get the picture. Now, one thing you may notice on this slide is we have rather many dead cats. And, well, that's not that pleasant. Thing is, we have this situation because of biology. In our universe, at least, and probably in all other relevant universes, if you have a dead cat and add more cyanide, you don't get a live cat. That's not how biology works, or chemistry, or anything. Luckily for us, cats and quantum computers are different in that aspect. So now we're getting to the actual meat of the matter. What we see here is called a Bloch sphere, and it's a representation of a qubit, a quantum bit. That's the equivalent of your zeros and ones, your bits, or your there is a current and there's no current, your green circle and your red triangle. This is the equivalent in the quantum computing world. So, what states can we have in there? Well, first of all, you can have a 0 state, which is represented by your vector pointing to the top there. You can have a 1 state, which is represented by pointing to the bottom. So that's simple enough, but you can also have something that looks like this. Now this isn't 0, and it isn't 1. It's not really between the two either, at least not in this visualization. It's somewhere on the sphere. And mathematically speaking, this is actually a combination of the two base values we're using. Now, if that math confuses you, because, I mean, zeros at the bottom, at the top, ones at the bottom, how can some of that be somewhere else? Ignore the math. We don't need it for the rest of the talk. It is a combination. It makes sense in the mathematical model. The Bloch sphere is a 3-dimensional representation of 4-dimensional space. It gets mathematical. We don't have to care about it. What we have to care about is, okay, assuming we have this qubit, what can we do with it? And if you want to do something with a qubit, you need a quantum gate. So let's go through a few quantum gates. The first one I want to show you is the so-called Hadamard gate. So the Hadamard gate operates on a single qubit, and basically it imagines that there's a further axis between the x and the z axis, and it then spins our vector around that axis. Now, if you are measuring a qubit, if it's at the 0 position, it will give you 0 all of the time. Binary value. If it's at 1, it will give you 1 all of the time. If it's somewhere in between, it will give you 0 and 1 with certain probabilities. So if we were to measure it at this point, in an ideal quantum computer at least, you would get 0 and 1 each with 50% probability. This state, where you can have 0 or 1 as a readout, is called quantum superposition. And we'll need that very soon. Another gate I'm going to show you is called the Pauli X gate. Now the X gate is much, much simpler to understand than the Hadamard gate, because basically if you have it at 0 and apply an X gate, it just takes the x-axis and spins it around there by 180 degrees, giving you the opposite value. So this is basically just a knot around the x-axis. Knot is easy enough to understand, right? But it gets more complicated if you go to another gate which incorporates part of what you know from the X gate now. So the conditional knot, or C-knot gate, is where things get really exciting. And basically, this operates on two qubits. We have the control qubit at 0 here, and we have the target qubit. And if we apply a C-knot with the control qubit at 0, well, nothing happens. Everything stays the same. If we have a 1 on the control qubit and apply the C-knot, it will flip. So basically, this is the behavior we know from the X gate. But what happens if our control qubit is in superposition? If it could be measured as 0 or 1? We get something like this. So we now have 2 arrows in that second qubit. Basically, it's a bit like this, because if you were to measure either of the gates, you would get the value of both gates. They are combined, they are locked together. If you have 0 in the first one, you'll get 0 in the second one because nothing happens. If you get 1 in the first one, you'll get 1 in the second one because everything happened. This is the situation we had with our radioactive isotope and our cat earlier. This is quantum entanglement. And quantum entanglement combined with quantum superposition is what makes quantum computers and quantum mechanics in general tick. Now, we don't actually have this until we measure. Before we measure, we basically just have both in superposition. And as long as they're in superposition, we can do some really funky stuff with these qubits. Now, I've shown you a few quantum gates, namely the Hadamard and the C-knot gate. I've shown you one of the 3 Pauli gates. There are Y and Z Pauli gates as well. They just spin around their axes by 180 degrees, those axes just being Y or Z. There's also stuff like the identity gate, which is the most boring gate ever because it just does nothing. There are phase gates, which are pretty exciting. You can do some pretty neat stuff with those. I'm not going to get into the phase gates today, but you can read up on them if you like. I'll have some material, some links for you later. And there are many, many other types of gates you can imagine. So, okay, we now know roughly how it works, but why do we need this? What are the use cases? And there are quite a few use cases, actually. For example, the big one that if you've heard anything about quantum computing, you've heard about this, it can break encryption. And it can break encryption because, at least in theory, it can break it because it's really good at prime factorization. Quantum computers can factorize numbers much more efficiently, in theory at least, than your regular binary computers can do it. If you want to know more about that, check out Shor's algorithm. Something you may not have heard of, various companies, including Google and Volkswagen, are using quantum computers now to assist them in engineering tasks. You could simulate molecules and atoms on quantum computers. You actually have a quantum state there. So you can easily work with quantum properties. And this can be really useful in research in physics and chemistry and medicine, of course. So this could be really, really exciting. Other than that, how about AI or machine learning? There are quite a few attempts to use quantum computers in those areas. And I think it's pretty safe to say that those will be some of the first fields that we as developers will really meet quantum computers, at least in the wild. Then you can use it for weather prediction. You can use quantum computers for pretty much any field that is nowadays aided by heuristics, because heuristics are just a shortcut because you are unable to calculate everything. But quantum computers will allow you to calculate, well, not everything, but much, much more than you can nowadays. Financial fraud is another use case that some people are looking into. Again, a field where heuristics is large. NASA is using quantum computers, early quantum computers, admittedly, in their engineering tasks. So that's similar to the Volkswagen case. And just to jump on the bandwagon, quantum computers could break Bitcoin. So if you have Bitcoins, you're probably safe for a couple of years until we have quantum computers that are powerful enough, but don't wait too long to sell them. Okay, so these are interesting use cases, I guess, but there's much more that could be done. Now, most people who nowadays are into quantum computers are scientists, physicists, as I said, engineers, etc. And they come up with solutions to the problems they know. We are the ones who will have to program them eventually. So we need people who are in the programming field, who are in the software development field, to have a look at quantum computers, try them out, work with them, see what they can do. We will come up with other use cases that so far nobody has thought of. And this is basically why I'm doing this talk today, because we have to get into quantum computing, and we can. So that's why we as a community should get into it. Why should you personally get into it? Well, there's this wonderful quote from Venkat. Basically, if you want to learn something new, learn something that's totally different from anything you know, because it will help you think differently. It's a wonderful quote, and believe me, quantum computer programming is different from what you know. So I'm going to show you two examples today of how you can actually today start programming for quantum computers. The first one I'm going to show you is the IBM Quantum Experience. So IBM has built real quantum computers, early prototypes, but they are real nevertheless. And they're basically offering them as a kind of quantum computer in the cloud service. How does that work? Well, first of all, the computers they built look something like this. And for the moment, yes, I hope they'll shrink considerably. Actually, this part here, most of that is a freezer. Well, a cryostat, but basically a huge freezer. The chip itself looks something like this. This is a 7-qubit chip. Those are the qubits here. And it has to be cooled down to, well, basically as cold as it can get, because they are based on superconductivity. And superconductivity, well, it works best if you have really, really cold states. Now, you can use this quantum computer, well, not that specific one, but ones that they're providing via their website. This is the entry site to the Quantum Experience. They have great learning materials there, by the way. So if you're interested in this later, you can check it out. It's great. Once you log in, the place you'll spend most of your time probably is this. This is called the Quantum Composer. And up here, we have information about the quantum computers that you can use. They currently offer for free, by the way, 2 different 5-qubit computers that anyone can use. They also have in their quantum experience, in theory, a 20-qubit quantum computer that's only open to their partners. And it gives you some information about those computers. Now, I think it's difficult to read, but the top quantum computer, it's cooled down to 0.012 kelvins. That's colder than in outer space. That's why they have this huge cryostat, that huge freezer. And as you'll see very soon, that's still not really enough. So the main part, however, is this part, the composer interface. And it's named so because it looks like, a musical score. And you do call the programs often quantum scores. Also, you have here your Q gates. Now, you'll recognize some of them. There's the H for Hadamard. There's the plus symbol, that's the C0. You see the green X, that's the X gate. And there are some other ones as well. So let's say we want to implement an algorithm in this. And we'll go with something we already know, Schrödinger's cat. Very simple algorithm to implement, not much logic in it, but it's a start. So what do we need apart from the cat? Well, we need our radioactive matter. We need our modified Geiger counter. We need our cyanide. And all of those have to be linked in some way. They have to be entangled. And if we lay that out in our quantum composer, it will look something like this. So the radioactive matter, we already learned that is in quantum superposition. So we can achieve that through the Hadamard gate. We then link all of the other items. So the Geiger counter and the cyanide and the cat through C0 gates. Because basically, if the Hadamard reads out as 1, that means that the radioactive matter has decayed. And in that case, all the other qubits should also flip. They all start out as 0, and if the first one flips, everything should turn to 1. And looking into the box is basically this pink symbol here, the measurement gate. In fact, let's measure all of the gates we're modifying here and see what we get. Now, you can run this, as I said, on a real quantum computer. It's sent to their quantum computer. There's a scheduling system, etc. And after a while, you get back your result. And your result, well, part of the result will look like this. So what does this mean? At the bottom, we have the various measurement values. Ignore the first value because that's the qubit we didn't measure. And what we see is here, this is the case where everything's 0, nothing happened. So that's a big peak. Back here, we have the case where everything happened. Everything's a 1. Cat's dead. And each of those two results come to about 30%. I think I ran this test 1,000 times. And you get 30% each, which leaves 40% of these results. So what are those? Well, those are measurement errors. See, this is still an early prototype, and it makes mistakes. And quantum error correction is actually a huge research field right now. Things are getting better, but you do have to keep in mind that you can't believe all of the results at the moment that you're getting. There is some randomness in there, basically due to the fact, among other things at least, that it's not at absolute 0. It is those 21 millikelvins above 0, which isn't much, but it's still a bit too warm. So that's the quantum experience. The other tool I would like to show you today is the Microsoft Quantum Development Kit. Now, this the IBM Quantum Experience is basically a drag and drop editor. You can write regular code as well. They have a programming language, and it translates back and forth between the graphical interface and that language. In most cases, at least for learning purposes, you will probably use the graphical interface. The Quantum Development Kit by Microsoft comes with a language called Q#. This looks much more like the code we're used to. And as I said, it's from Microsoft, so initially it was only available for Windows, and I thought during the preparations for this presentation I'd have to tell you, well, if you have anything but Windows, tough luck. But about a month ago they said, hey, it's now available for Linux and macOS as well, so everyone can download it, everyone can start playing around with it. Yes! Okay, so you can do it. Let's have a look at what it looks like if you actually do it. So the language Q# is heavily inspired by other .NET languages, as you would assume, and it does actually run inside a .NET environment. Here we have a very simple program. Most of it's blurred out at the moment. It's not something about your eyes. It really should look like that. And we'll go through the program step by step. So what do we have? First of all, here we're applying a Hadamard gate to our isotope, H isotope. And then we apply the C0 to the isotope and the Geiger counter. And another C0 to the Geiger counter and the cyanide, and another C0 to the cyanide and the cat. You know this. And it's just written down as code. It's the same algorithm as we did before. What else do we have? Because there's obviously more code. Well, first of all, we define a mutable value, what we would call a variable in most languages. Most things in Q# are immutable by default. We want this to be mutable. And this variable is supposed to represent the state of the cat. Is it alive or is it dead? This is a simple 1. It's not a qubit value. This is a binary value. Here we check in the box whether the cat is alive or dead. M is the measurement value. This is the pink thing you saw in the Quantum Experience. Same concept. And then at the end we return, is the cat alive or is it dead? Okay, simple enough. What else do we have? We have boilerplate, basically. So here we say this algorithm needs 4 qubits. We have to state explicitly how many we need. They will be provided by the language. Then we give them proper names. Normally you have an array of qubits, and that's fine initially, but you can't throw best practices out of the window just because we have a new language here. We do have to give the qubits names so we can understand what we're doing. Then we initialize them all to 0. The Quantum Experience did this for us. Everything was initially set to 0. Q# does not do this for us. We have to do it manually. And at the end, we're setting them back to 0. Now, the reason we have to set them to 0 initially and at the end is basically decay. Quantum decay means that a qubit will always strive to some kind of equilibrium state. We want to make sure it's not in equilibrium, but rather it's in a defined state that we can work with. And you could leave out, language-wise, the initializing to 0. Then you would just get random results. Q# forces you actually to set them back to 0 when you're finished. And that's basically all of the Q# code. Now this runs in the .NET environment, which means we can access it from other .NET languages. And so here we have a few lines of C# code, which basically say, well, here, create a quantum simulator to run my algorithm in. Run the algorithm in that quantum simulator, and then tell me what the result is. And you can run this code on your computer. It runs it just this once, in this case, and it'll either tell you the cat's alive or the cat is dead. And that's it. This will run on your computer. So we have a quantum simulator here, and that may beg the question, then why don't we just simulate it? Why do we need a real quantum computer? It obviously works, so why don't we just simulate everything? And don't have those measurement errors, we don't have the hassle. It's a huge financial investment that companies like IBM, for example, and many universities are taking on. Why do they care? And I'd like to go back to a previous slide to answer that question. Remember this slide? Now, in theory, the slide is designed in such a way that when I press my button here, it will have a smooth transition from the dead cats to gravestones. I clicked. Yeah, that wasn't smooth. My computer is having difficulties with PowerPoint. And what stress would a quantum computer put on a binary computer? Well, IBM actually looked into this issue, and they published a paper last year. They had two quantum computers that they simulated. One of them was a 49 qubit computer, and they needed 4.5 terabytes of RAM. One of them was a 56 qubit computer, and that needed 3 terabytes of RAM. Note that this wasn't the same algorithm, and maybe the algorithm they used for the latter was more optimized. It's still much more than we have on our development machines. There are computers with that kind of memory available, of course, but you don't have them sitting at home, I would assume. If you do, let me know. I might come by. So this was a huge success, and you'll see why it was a huge success with this line here. Previously, those kind of simulations would have needed 8 petabytes of RAM for the 49 qubit machine and an exabyte of RAM for the 56 qubit machine. Let me repeat that. 1 exabyte of RAM. Can you imagine how much an exabyte is? Probably not. So let me break this down for you. 1 exabyte is 1,000 petabytes, which is 1,000,000 gigabytes, terabytes, sorry, which, depending on whether you speak British or American English, is 1,000,000,000 or 1,000,000,000 gigabytes. That's 10 to the 18 bytes of RAM. So 10 to the 18 bytes, that's hard to imagine. Our universe, according to current estimates, is 13.7 times 10 to the 9 years old. That translates to 4.32 times 10 to the 17 seconds. That's less than half the amount of bytes we have in an exabyte. So the improvement that IBM made there by getting it down to the terabyte range is astonishing. But as the number of qubits grows that you have to emulate or simulate, and as the algorithms grow that you want to simulate on those simulations of quantum computers, things will get, well, even more unrealistic than they are right now. So, at least for the time being, we are stuck with actual physical quantum computers. Now, this here is a 50 qubit quantum computer that IBM built. And until recently, I thought this would be the largest machine I'd be able to show you. About 2 weeks ago, Google came along and said, hey, we have this thing here. We call it Bristlecone, and it has 72 qubits, and apparently very low error rates. Now, when they announced it, the testing wasn't fully completed, so we can't be absolutely sure what the error rates look like, but it's promising. Note the 50 qubit machine I showed you, I think that was from earlier this year. This is from 2 weeks ago. Things are moving really rapidly. And IBM and Google aren't the only companies in the game here. For example, Intel is also working on quantum computers. At the beginning of the year, they introduced a 49-qubit quantum computer after some previous iterations. The largest one in the picture is the 49-qubit one. And Alibaba, the Chinese internet giant, announced in early March that they were offering a quantum computer in the cloud similar to what IBM is offering. Now, as I said earlier, IBM to certain partners offers a 20-qubit computer. This here, offered by Alibaba, is an 11-qubit computer, which is the second largest one available. At least it's available to some people. I registered with Alibaba, looked for anything, and I could only find this announcement. So apparently it is available in theory, but only to, well, probably members of the university with which they are doing this, or the research institution, I should say. But things are going to happen. Quantum computers will become more and more available in the next months and especially years. And so this is the breaking point. This is the point where people like us have to get started and can get started with quantum computing. So if you want to get started, what can you do? Well, as I said earlier, there's the Quantum Experience. You can register there. It's all free. And they have great learning material. Here's the URL. I will make the slides available online, so you don't have to remember that URL right now. Great tool for learning. There is, as I said, the Microsoft Quantum Development Kit available for. Yeah, sure. I'll still speak about the next slide. There's the Microsoft Quantum Development Kit available for Windows, Mac, and Linux. This also is absolutely free of charge and available under this URL. If you want to take pictures, now would be the time. And also, about 1.5 weeks ago, Stack Exchange, who run this tiny site called Stack Overflow, you may heard of, they opened a private beta for a quantum computing site. Now, it's a private beta, so you can only join by invitation. If you want to join, let me know. I can get an invitation to you, and that's well. The site is at this address, of course. My invitations aren't, but just let me know. And, well, apart from that, I would say it's time to explore. Try these tools, play around with them, read the tutorials. There's much, much more than I got to cover today in the information material provided by, for example, IBM and Microsoft, and of course other sources. Play around with it, and hopefully we'll get some really cool results. And now, ask your questions. That adds two numbers. That's a good question. If you want to add two numbers, well, in theory, a very simple adder would be just a C0. If you have 0 and 0, you get 0. If you have 0 and 1, you have 1. If you have 1 and 0, you have 1. If you have 1 and 1, you get 0 because of overflow. But you always have the problem of measurement error here. You probably don't want to build something like an adder in a quantum computer. The profile of quantum computing applications, for one, as I said earlier, is anything that's nowadays, or many things at least, that nowadays you would improve with heuristics. So you'll probably be able to improve those with quantum computers. Among these things are, well, prime factoring, of course. You can do that. Nowadays, you would basically have to try all possible combinations, and you can improve that with heuristics, but it's difficult. Another issue that can be solved with quantum computers is unstructured search. There's an algorithm called Grover's algorithm, where basically if you have a data set and you know nothing about how it may or may not be sorted, with any regular binary computer, you would have to look at each separate entry and check, is that the one I'm looking for? Is that the one I'm looking for? Is that the one I'm looking for? If you have n entries, you'd need potentially n tries. It's certainly an O of n. Grover's algorithm can do it in O of square root of n. Basically, by using this, this state of superposition and looking at several values at the same time. So anything that goes into the area of breadth search is a potential candidate as well. And there are probably many, many other problems you can look at that so simply nobody has really looked into yet. I'm pretty convinced that it's possible to write a proper sorting algorithm with a quantum computer. I haven't seen anyone do it yet, and I haven't been able to come up with one myself. But I do think it's possible. We just have to find the proper algorithm. Okay. Mm. Okay, so basically the question is, can quantum computers help with floating point decimal representation? Infinite floating points. The answer is, I don't know. Maybe there's a way. I haven't seen anything about that so far. In theory, I would say it is possible because you could choose some kind of representation within the Bloch sphere, where each point on the sphere is a possible value, and that, in theory at least, would be infinitely many values. Measuring those is a bit more difficult because you get either 0 or 1. So I can't think of a way to represent infinitely long binary number floating point numbers off the top of my head, but that doesn't mean that there isn't a way to do it. Yeah. Mm-hmm. Mm-hmm. Okay, so basically, how do you represent numbers at all in a quantum computer? Um, Basically, the same way, at least you can do it the same way you do with a binary computer, because when you measure your values, they will be 0 or 1. You don't get a value on the sphere. You get 0 or 1s with certain probabilities. There may be better ways of representing numbers in quantum computers. Again, I don't know. It's something you can certainly look into. There probably is a better way to do it. But we're in the early stages where that kind of question is still something that, as far as I'm aware, hasn't been fully answered. So you can go with a basic representation where zeros and ones give you your result, just like with a binary representation on a binary computer, and anything from there onwards is up to research. Yeah. Mm-hmm. Mm. Okay, so how do qubits work on a technical level? I'm no expert in this field. Basically, I can tell you that there are at least, I don't know, 4 or 5 different ways in which people have started building qubits. The superconducting method that is used by IBM and Google and quite a few other hardware manufacturers is currently the most successful method. How exactly that works, I'd have to check myself. There are some other ways that don't necessarily require supercooling, and those could be very promising in the long run, because basically, if you want to have a quantum computer with you, if you want to have it in your laptop, in your car, in your phone, you don't want to have, a huge cryostat that you have to carry with you. You don't want to have to cool it to as close to absolute zero as you can get. Currently, to my understanding at least, those technologies aren't as advanced as the superconducting methods, and so we'll have to see where those go. Does that answer your question? Great. Any other questions?
If nobody asks.
Yeah, sure.
So in the services like IBM, Microsoft, our code will be run on simulations, I guess, not on the real quantum.
With Microsoft, yes. With IBM, you can run it on a simulator. Basically, you have 2 options. When you have your code in the Quantum Experience, you can choose the simulate button, and then it'll run not automatically. It'll run immediately on a simulator, and you'll get back your result in no time. You can, say, run it on the real quantum computer, and they have a scheduling system. I'm not going to get into it. It's easily explained. And then they do send your code to the actual quantum computer they have in their facilities. Will run your code there, and after a while you get back your result. And this is actual quantum computing happening. That's what we saw when I showed you the results, where we had all those errors. If you run it on the simulator, you get much nicer results. Which is great for testing, but of course, if you want a realistic image, you should run it on the real device. Okay, anyone else? Yeah. Can a quantum computer generate truly random numbers? My guess is yes, it can. I'm no expert in randomness, I must admit. So you would have to ask someone who's more familiar with what constitutes true randomness. But to my understanding, yes, it can. Okay, anything else? In that case, thank you for listening. And no cats were harmed in the making of this presentation.